to alternating current part 5, and this is the last part of all the alternating current that we have done. Those points which have been struck through, these were completed in the previous parts, in the previous videos. Okay, we have done all those things in those 4 parts. Okay, and our today's class will be only concentrated on to this last part, that means the transformer. So we will try to do transformer in details, okay, about its principle of their components required, then construction, then working and all. Okay, so transformer, what is meant by transformer? Transformer is an electrical device which converts lower alternating voltage at higher current into higher alternating voltage at lower current, and vice versa. Okay, vice versa means it can be just the opposite. That means from converting from higher alternating voltage at lower current to that of lower alternating voltage at higher current. So this term, okay, or this word at higher current, lower current, this is very important. When we try to change this alternating, okay, voltage, okay, into high alternating voltage, it is at the cost of the current only. Okay, current can be varied depending upon that what happened, voltage will also change, provided that the power remains the same. Okay, the power remains same, that means output power and input power remain same. So let's go directly to that of the principle. What is the principle of working of this transformer? Transformer is based on the principle of mutual induction. We have already learned about mutual induction, that whenever changing of current takes place in one circuit, and if that change in the magnetic flux, if it is link, okay, and if due to that of the link induced magnetic flux, if induced EMF is developed in the other coil, then that phenomenon we call it as mutual induction, right? So it is a phenomenon of inducing EMF in the secondary coil, okay, due to the change in the primary coil, and hence the change in the magnetic flux in the secondary coil. So what is this mean by primary coil and secondary coil? Now let's directly go to that of the construction first, and then I will come back again here. So transformer consists of laminated soft iron core, okay, laminated soft iron core which is made with the thin soft iron sheets, and it is made in the form of rectangle like this. Actually it will be of 2 pieces of L, and if that 2 pieces of L just like this, this is 1 piece, okay, of L, the shape L, I mean capital L, and another L will be here like this. Got it? And if they make it one after the another, then it will be just like that of a rectangular coil. While we are making such sheets of this L shape soft iron rectangular core, so as to have that less eddy current, okay, that eddy current decreases the amount of electrical energy. So in order to prevent from that loss of that electrical energy in the form of eddy current in this big or huge size core, we are making that laminated one. And moreover, this laminated soft iron core are insulated from one another by means of that insulating material that like that of varnish. Okay, now that laminated soft iron, okay, core is made in this way, and one coil is wound on the one side of that rectangular core, and the other coil is also wound on the other side of that rectangular soft iron core. Okay, wherever the input is fed in one coil, okay, that coil will be known as primary coil. Okay, so this is the input AC, and so this input coil we will call it as primary coil. And wherever that output is taken out, output AC current is taken out, that coil we call it as secondary coil. And this output current is taken out across a lot or high resistance known as lot. So across these two, one terminal here, another terminal here, the output will be taken out from it. Okay, So what happened when that AC current is passed through this primary coil? We know that AC current is that type of current which changes its magnitude continuously and changes its direction periodically, right? So whenever that magnitude of the current changes, the magnetic flux that is produced here will be also linked here. Okay, so whatever the change of magnetic flux here, that will be also what link with this secondary coil. And so whatever the induced EMF that is developed here into the secondary coil, it is due to the change in the current in this primary coil. So this phenomenon we call it as what induced mutual induction, I mean. That means the induced EMF is developed in one coil due to the change in current in the other coil. We call it that phenomenon as mutual induction. So the principle of the transformer is what? Nothing but mutual induction, right? Let's go to the theory part now. Now let's take it that EP is the induced EP is the applied EMF, and that applied EMF coming from the source, okay, AC source, that will be the applied EMF here. So EP is nothing but this is the EMF applied in the primary coil, at the primary coil. So we know that due to the self-induction, what happened, your EP will be equal to what? Rate of change of magnetic flux. Okay, if the total number of turn here in the primary coil is denoted by NP, then it will be equal to what? EP will be equal to minus of NP d phi by dt. This is given by your Faraday's second law. Okay, Faraday's laws of electromagnetic induction, rather Faraday's second law of electromagnetic induction, and this minus is due to that of your Lenz's law, right? So what happened, your this d phi by dt, okay, this is a rate of change of magnetic flux. This rate of change of magnetic flux here, it will be same as it is in the primary coil. That much rate of change of magnetic flux that will be linked here through the secondary coil, provided that there is no leakage of magnetic flux. Okay, if there is no leakage of magnetic flux, then the rate of change of magnetic flux produced here, that will be also same with the rate of change of magnetic flux here. But as the number of turns are different, it will have the different output potential. Now if your total number of turns in the primary coil is denoted by NP, that total number of turns in the secondary coil, let's denote it by NS. So the induced EMF that is developed in the or set up in the secondary coil will be also equal to that of rate of change of magnetic flux, okay, times the total number of turn in the secondary coil. Okay, that is what it is given here. So both are applying that second Faraday's second law of electromagnetic induction, and this minus is due to that of Lenz's law. Now what happened, as we have considered that there is no leakage of magnetic flux, then what happened, we will have to take it that the rate of change of magnetic flux is same. Suppose if that of from the first equation, okay, if you take it this as a first equation, then what happened, your EP divided by NS, this will be equal to what? Let's put it 1 minus here, so d phi by dt, right, from the first equation. From the second equation also, your ES divided by NS, this will be equal to what? D phi by dt minus d phi by dt, right? So as I told you that the rate of change of magnetic flux in the primary coil, that will be equal to the rate of change of magnetic flux in the secondary coil, right? So both are same. So by equating these two, what happened, you will get it that EP by NS will be equal to ES by NS. Then what happened, that one, after equating it, then you will get it that this equation, the last equation, ES by EP is equal to NS by NP. We call it this ratio as transformation ratio. Depending upon this value, that transformer will be of step up or step down. That will depend upon this transformation ratio. Okay, if this transformation ratio capital K is greater than 1, then we call it that as step up transformer. and if this K is less than 1, then we call it that as step down transformer. What is meant by step up transformer and what is meant by step down transformer, I will tell you. Step up transformer is that type of transformer from which, okay, the low input voltage is met to high output voltage. For example, for the working of that X-ray machines and all, we cannot use this 230 or 220 volt, okay, from the incoming source. Rather, we need to have that of thousands of volt. Suppose, for example, from 220 volt, okay, from 220 volt we want to get it that of 1000 volt. For example, if we want to have this 1000 volt, then we need to use what is called as step up transformer. Okay, in the step up transformer, from low to high, that is step up. In the case of what step down transformer, say for example from 220 volt, you will have to get it only the output of 12 volt, then such type of transformer we call it that as step down transformer. Got it? Step down transformer, that means from high to low, that we call it as step down. Got it? So depending upon this number of turns, okay, of the primary coil and the secondary coil, we need to change it. Okay, so if this K is greater than 1, then we will call it that as step up transformer. So if this K is greater than 1, then what happened? The ratio of the total number of turns of the primary coil of the secondary coil to that of the primary coil, this will be greater than 1, means what? The number of secondary coil must be very large, okay, when you compare with that of the primary coil. That means total number of secondary turns will be more than that of the total number of primary coil. Then what happened? That type of transformer will be called as what? Step up transformer. If the total number of turns, okay, on the contrary, or on the other hand, if the total number of secondary coil is less than that of the total number of the primary coil, then that type of the transformer we will call it that as step down transformer. Got it? If this total number of secondary turn is less than that of the primary coil, naturally the ratio of this will be less than 1, so your K is less than 1. Okay, transformation ratio is less than 1, so we will call it that type of transformer as step down transformer. So all those things will be coming up here. Okay, now we call it this ratio either that of the output voltage to the input voltage, or the ratio of total number of turns of the secondary coil to that of the total number of the primary coil. We call it this as transformation ratio. So depending upon this, there will be two types of transformer, as I said. If K is greater than 1, transformation ratio greater than 1, then what happened? That type of transformer is known as step up transformer. If this K is less than 1, then we will call it that as step down transformer. In the case of step up transformer, what happened? The total number of secondary turns will be very much greater than that of the total number of turns of the primary coil. In the case of step down transformer, what happened? This number of turns in the primary coil will be more than that of the total number of turns in the secondary coil. Got it? So for an ideal transformer, okay, for an ideal transformer, we assume that the output power is equal to the input power. This happens only when there is no leakage of that of magnetic flux. Okay, but in the actual case, there is always a leakage of this magnetic flux. Okay, but if we assume that the transformer is an ideal one, then output power will be equal to the input power. What is output power? Output voltage times the output current. We call it that as output power. Input current times the input voltage, we call it that as what? Input power. So your input current and input voltage, the product of these two, we call it as input power. Likewise for output power also. So if we assume that there is no leakage or no loss of the magnetic flux, then what happened? Output power must be equal to input power. So from this equation again, if you try to express it ES by EP, then it will be equal to what? IP by IS. So these can be again related as what? Input output power by input, output voltage by input voltage is equal to what? Output total turns, okay, in the secondary coil to the input number of turns, that means NP. This can be again equated as IP by IS, okay, that means input current to the output current. So this we call it as what? Your transformation ratio. So your transformation ratio K can be expressed as what? Your transformation K, okay, transformation ratio K can be expressed as what? Output voltage to the input voltage. This is also equal to the total number of turns of the secondary coil to the total number of turns of the primary coil, and it is also equal to the input current to the output current. Okay, so you can correlate this transformation ratio in terms of the voltage, ratio of the voltage, ratio of the total number of turns, or ratio of the currents, like this. But don't confuse it here in the case of the voltage and the total number of turn. It will be first with the output to the input, output to the input, but here in the current it is what? Input to the output. Got it? Input current, that means primary current, to the output current, secondary current. Got it? Now what is meant by efficiency? Efficiency is nothing but this is the ratio of that of the what? Output power to the input power. Now when you learn in class 10 about that of the magnification is nothing but the efficiency, okay? Output to the input. Output is what? The image. Input is what? The object, in the case of that magnification in light, okay, in your class 10. So magnification is defined as what? Image distance by object distance, or it may be what? Size of the image to the size of the object. So size of the image is what? Your output size. Size of the object means what? Input size. Okay, so output by input, we call it that as efficiency. You can remember in that way, okay? Just I'm telling you one of the mnemonics, okay? If you have another mnemonics so as to remember this formula, then you can use it, that one also. So your efficiency, it is denoted by eta. This symbol is not an English letter, rather this is a Greek letter. We call it this just like N, small letter N, okay, English letter I mean. If you pull little bit downward like this, then it will be what we call as eta, okay? In English word we call it this as eta, okay? This is not an English letter but rather a Greek letter, okay? So eta is defined as what? The ratio of the output power to the input power. But if that ideal, if that transformer is considered as ideal, then we take it that output power is equal to input power, then this will be equal to what? 1. So 1 means what? In terms of percent, it will be 100%. 1 into 100%, that means 100, right? So for an ideal transformer, your efficiency is assumed as what? 100%. But in the actual practice, there will not be that much, not that much 100%, okay? So let's see once more again about that of step up transformer and step down transformer, okay? Whatever I have told you, then it will be all coming up again here. So the first one is of step up transformer, and the second one is of that of step down transformer. As I told you that in the step up transformer, the number of turns in the secondary coil will be more than that of primary coil, right? NS is greater than NP, so what? K is greater than 1. So this will be what? Your step up transformer. So in this case, what happened? If you correlate all those formulas, ratios of those potential, turns and currents, okay, then you will have it that ES is greater than EP, IS is less than IP. That means your secondary current is less than primary current, okay, input current. So what happened? That amount of the high voltage, okay, that is obtained here. Input is of low voltage, output is of high voltage. So high voltage means what? This increase in the voltage is at the cost of the current. So what happens if the output voltage is high, then output current will be low. Got it? So as to have that constant power, the product of the potential and the current here, that will be also the product of the current and the voltage here. Got it? So what happens when ES is greater than EP? That means if the output voltage is more than the input voltage, then what happens? The current here, okay, the secondary output current will be less than that of the input current. Similarly, okay, it will be also in the case of step down transformer. In the step down transformer, what happens? Number of the output turn will be less than that of the input current, input coil. And what happened? The current here, it will be very high, but output current will be high and the input current will be low. So that is what it is happening here. So what happened? As the total number of secondary coil is less than that of the primary coil, naturally their ratio, which is known as transformation ratio, is less than 1. So what happened? ES, secondary voltage or output voltage, is less than that of the input voltage. And you can also say that this secondary current or output current is very much greater than that of the input or primary current. So this happens, okay, and this will be of the types of the transformer. There are two types of transformer depending upon the voltages of the output, okay. That is of high transformer, step up transformer and step down transformer. There are other type of transformer also, other type of transformer also, depending upon which type of transformer will be used in what situations, okay. That will not be under your consideration in your syllabus, so that is out of syllabus, so we will not discuss it here, okay. And let's try to discuss about the energy losses in a transformer. If there had been no energy losses, okay, during this transformation of high voltage to low voltage or from low voltage to high voltage, then we might not have necessary to consider about these energy losses, okay. If this transformer is an ideal one, then we will not require to discuss these energy losses. But as I told you that in the actual practice there is always loss of energy. The efficiency of transformer can never reach that 1 or 100%. So that means there is always some loss of energy during transformation of this electrical energy from high voltage to low voltage or from low voltage to high voltage. So let's see. The first one is known as copper losses. What is meant by copper losses? Actually, the turn of this primary and a secondary coil, these are actually made up of copper. You can make it by other material also. Generally, at that time when transformer was discovered, okay, we use it with the copper wire, and still in many of the transformer we have been still using this as copper wire. So whatever the loss of heat, okay, that is produced by this coil, okay, when that there is a transformation, okay, we call it that amount of loss of heat as what? Copper losses. You know that your Joule's heating effect, H is equal to I square RT, right? This coil will have some certain inherent resistance, okay. Likewise your secondary coil will also have certain inherent resistance. If you make it increase the number of turns, then longer coil will be required. Longer coil means what? Larger resistance. So what happened? Due to that flow of current, okay, onto this conductor which has its own inherent resistance, there will be always loss of heat energy. That loss of heat energy due to these coils, we call it collectively as copper loss, right? Then what happened? The another one is what? That is a flux losses. I told you that there is always leakage of magnetic flux when the transformation or the flux, okay, that is linked from the primary to the secondary, there will be always leakage of this flux, and this leakage of flux, we call it that as flux losses, okay. These flux losses can be minimized by winding the coils over one another. If this coil is wound, okay, very closely and Moreover, if these coils are wound one above the another, we call it that as coupling. No doubt here also it is coupling, but the coupling is very far away. One primary coil here, secondary coil far away. Instead of this, if this secondary coil is wound over to this primary coil, then there will be what decrease in the loss of this magnetic flux losses. Okay, so your flux losses or leakage of flux losses can be minimized if these two primary coils and secondary coils, if they are wound one above the other, then that leakage of flux can be minimized. Okay, in the next one, let's see about that of the iron losses. Iron losses may be of two types. Okay, the first one is eddy current losses and the another one is hysteresis losses. Now what is meant by this eddy current? Eddy current is that type of current developed in the conductor itself, of large dimension conductor itself, whenever there is a change of magnetic flux. So whenever a conductor of large dimension, if it is subjected to what changing magnetic flux, then what happen, induced EMF is developed and induced current. Due to that induced EMF, induced current is set up to flow onto that conductor itself. In the conventional current, we know that current flows from one end of the conductor to the other end, right? But in this eddy current, what happened? Eddy current is that type of current which flows inside the conductor itself. Okay, in the conductor itself, whenever that conductor is subjected to changing magnetic what flux. Now the very example of eddy current is there in the induction furnace, and that of your induction cooker, that is done with the help of this eddy current. Got it? So when a magnetic changing magnetic flux is linked with that iron core, you know that core is iron. Okay, and if that changing what magnetic flux is linked with that iron core, then what happen, eddy current are set up, which in turn produces heat, and heat that is coming from where? From the electrical energy. So electrical energy is wasted. So in order to minimize this what eddy current, we use laminated soft iron, and instead of taking that rectangular shape what core, we use that type of L shape, right? Laminated sheets. So that what happen, when eddy current cannot be reduced to zero. Eddy current cannot be totally removed. Okay, eddy current will be flowing there, no doubt, but as the dimension is of not that of large one, eddy current will be only flowing there onto this L shape like this. Okay, so what happen, if that eddy current is allowed to minimize, instead of flowing here like this, okay, you will allow to flow only through this small rectangular shape like that only. Got it? So what happened, we can minimize it, that eddy current. So the wordings are all given here. You try to copy it after pausing the video. Okay, and another loss is what? Hysteresis loss. Hysteresis means what? Whenever that changing magnetic flux, okay, if is met, okay, in the positive side, what happened, during the positive side it is magnetized, during the negative of the AC it is demagnetized again. So this soft iron core is placed into what, or subjected into what, a cycle of magnetization and demagnetization, and this process we call it, okay, that as what, hysteresis cycle. So whenever this what hysteresis cycle takes place, because of that of magnetization and demagnetization, there will be always a loss of energy, and that loss of energy due to this magnetization and demagnetization process, because of that positive half and negative half of AC input, there is always a loss. We call it that loss as hysteresis loss, and to minimize this hysteresis loss, okay, it can be done by using what, suitable material with thin hysteresis loop. Okay, with thin hysteresis loop. If you are taking that hysteresis loop of what, of larger area, just like that of steel okay, just like that of alnico, then what happened, hysteresis loop will be very wide, and this loop area is directly proportional to the amount of energy spent during magnetization and demagnetization. Okay, but if you use it, that hysteresis loop of that of soft iron, then the loop area will be very small and thin like this hysteresis loop. Then what happened, this area is directly proportional to the amount of energy spent during that what magnetization and demagnetization process. Okay, but if it is of thin one, this is for soft iron. Okay, the amount of energy spent during magnetization and demagnetization will be small, but if you use it that of alnico or steel, then what happen, the area will be wide like this. Okay, so this is for that of steel or alnico for making what, permanent magnet. Okay, for permanent magnet, so that will not be required. Okay, such type of core material are not what advisable. So rather we will have to use it the soft iron core in the case of transformer. Why? Because to minimize the hysteresis loss, right? And next is what, next is the loss due to the vibration of the core. Now whenever you visit near the transformer, then you will hear some humming sound like that, like that. That humming sound is not from some other source, rather it is from that of what, this core of the transformer. So that core of the humming sound, you know that sound is a form of energy, right? And that form of energy, by conservation of energy, that cannot be come out of from nothing. So that sound, that vibrational sound or humming sound, that is coming from the electrical source only. So some amount of energy is always lost due to that vibration of the core or that giving out of that humming sound. Okay, so that is also one of the loss of this humming sound, but we cannot neglect it, these reduce this humming sound. It will be always there in almost all the types of the humming sound, almost all the type of what, transformer. So we call it this as what, the loss due to the vibration of the core, or you can call it this as magnetorestriction effect. Okay, so these are the different type of the energy losses, and with this we come to the end of our today's class. Thank you for watching my video.